Hello, we are the group 5 from the classes of F4AS 1 to O4 12. We will be presenting about electron microscope, and this presentation will be present to Dr. Azlina. Hi, my name is Muhammad Nazri, and let me introduce about electron microscope. An electron microscope is an advanced instrument that uses a beam of electrons to produce highly detailed image of microscopic objects. Compared to optical microscope, it offers much higher magnification and resolution, allowing scientists to observe structures at nanometer scale. Electron microscopes are widely used in geology, nanotechnology, and material failure analysis to study material composition, surface structures, and defects that cannot be seen with conventional microscopes.
Let's begin with the basic theory. Traditionally, optical microscopes rely on visible light photons. However, light has a relatively long wavelength which creates a physical barrier called the diffraction limit. To bypass this, electron microscope operates on the principle of wave-particle duality. Since moving electron acts as a wave and carry wavelength up to 100,000 times shorter than light photons, they allow the instrument to achieve an incredibly high resolution that easily surpasses ordinary optical limits. Next, let's look at the basic internal components required to handle these properties. Instead of a light bulb, the system uses an electron gun to emit a stable beam of electrons. Furthermore, because electrons are physical, charged particles, they cannot pass through ordinary glass lenses. Therefore, the instrument utilizes electromagnetic lenses by dynamically tuning magnetic fields. These lenses can accurately bend and focus the electron beam. Crucially, this entire framework is sealed inside a high vacuum chamber, ensuring that the electrons do not crash into air molecules and scatter before hitting their target. Now, how do these components function together as a single system? The mechanism happens in three continuous phases. First, the electron gun generates and accelerates a high voltage beam down the column. Second, the electromagnetic lenses tightly focus and condense this beam onto the specific area of interest. Finally, when the electron strikes the specimen, they interact with the atoms of the sample, creating signals that are called by specialized detectors to construct a high magnification digital image. That summarizes the basic scientific principle and mechanism of this technology.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Wazif bin Huzarin Diliza and my student ID is 2024-679-786. So now I'm going to talk about the evolution of electron microscope. So it all started in 1931 with the very first concept of an electron microscope. Scientists realized that using electrons instead of light wave could completely shatter the resolution limits of traditional microscopes. Fast forward to 1940, when Vladimir Zurkin introduced the first electron microscope in the United States. This absolutely beast of a machine weighed half a ton, but it was a game changer, achieving an unprecedented magnification of 100,000. By 1965, the technology became commercially viable with the introduction of the first commercial scanning electron microscope, or SEM, allowing scientists to see the detailed 3D surfaces of microscope structures. Then came the digital revolution of the 1980s. Computers were integrated to enable automated control of electron microscopes, vastly expanding what they could do and making them much easier to operate. Right around the same time in 1981, a massive breakthrough in biological imaging occurred. Alasdair McDowell and Jacques Dubois at European Molecular Biology Laboratory reported the first successful implementation of cryo-EM, a technique that allows us to look at biological samples in their native frozen states without destroying them. In 2005, imaging took another massive leap forward with the development of 4D, ultra-fast electron microscopy. This literally adds another dimension to imaging, letting scientists capture not just static structures, but atomic scale processes changing in real time. And that brings us to present. Today, the resolution limit of the transmission electron microscope has shrunk down to just 1 nanometer, boasting a mind-boggling maximum magnification of approximately 1 million. We are truly looking at the building blocks of matter itself. It's like we are going to talk about the core scientific principles behind how an electron microscopy actually works. Number 1, electron beam generation. Instead of a light bulb, the process starts with a specialized source, usually a heated filament, that generates a highly concentrated beam of accelerated electrons. Number 2, electromagnetic lens. Since we are using light, regular glass lens won't work. Instead, we'll use electromagnetic lens to focus and control the path of the electron beam. Next one, vacuum environment. This entire process must take place inside a strict vacuum. Without it, the electrons will collide with air molecules and scatter, ruining the image. Next one, electron sample interaction. The focus beam hits the sample as the electrons interact with the specimen. They scatter or knock out other electrons, creating signals containing detailed structural data. Last but not least, image formation. Finally, these signals are captured by detectors and processed by a computer to form the incredibly high resolution images we see.
Next, I'm going to talk about some real-world applications of this technology. First, in medical and biological research, it is used to study very tiny things like viruses, bacteria, and cell structures that cannot be seen clearly with a normal microscope. This helps scientists understand how these microorganisms work and how diseases affect the body. It is also very useful in medical diagnosis, biomedical research, and even in developing new medicines. Besides, this technology is also widely used in semiconductor industry. It helps engineers inspect microchips and electronic components in a very detailed way. Through this, they can detect a small defect or problems during the manufacturing process. As a result, it helps improve product quality and make sure the electric devices produce and work properly. Other than that, this technology is also used in material science. It helps researchers examine the structure and surface of different materials in a very detailed way. By doing this, scientists can understand the properties of material better and use that knowledge to develop more advanced material. It is also very important in the field of nanotechnology, where scientists work with extreme small structures and particles. Other than that, it is also used in forensic science. In this field, it helps experts analyze tiny evidence such as fibers, particles, and gunshot residue that may be found at a crime scene. This small piece of evidence can provide important clues during an investigation. So basically, this technology plays a big role in helping forensic experts carry out criminal investigations and analyze evidence more accurately.
My name is Farhan Rubel bin Hisham, 2024251064. I will talk about potential of electron microscope. The first one is massive magnification. While a good light microscope tops out at around 2000 times magnification, an electron microscope can magnify specimens up to 1 million times or more, allowing scientists to view individual atoms. Next is virology and microbiology. It allows for the direct visualization of virus structures like the spikes on coronavirus, bacteria, and cellular organelles. There is mitochondria and ribosomes. The last one is cost and complexity. These instruments require specialized rooms, there is ferromagnetic interference and vibrations, and cost hundreds of thousands to millions of dollars. The trend is moving toward desktop or benchtop shapes, that is, uh, electronic microscopes, making basic electron imaging much more accessible to smaller universities and labs. In summary, the development of the electron microscope has fundamentally transformed our ability to observe and understand the microscopic world. By overcoming the physical wavelength limitations of visible light, this technology leverages the principle of wave particle duality and the vastly shorter wavelengths of accelerated electrons to shatter traditional resolution boundaries. Through highly synchronized orchestration among its core components, including high-energy electron sources, electromagnetic focusing lenses, and strict vacuum systems, electron microscope capture intricate atomic-level data and convert it into high-definition digital imagery. That's all from us. Thank you.